Swayam Prabha. Digital India. Educated India.
Okay, so let us continue our analysis of cooling of a body in a reservoir. So, we took the problem in which we had a solid body which was initially at temperature T 0 and it was immersed in a reservoir of temperature constant temperature T infinity. We determined the model equation as dt by dt is equal to minus H A S rho V c times t minus t infinity and solved some of the problems in which, for example, we were asked to give the equilibrium solutions or equilibrium temperatures. So, let us quickly see what we arrived at. We arrived T equilibrium as T infinity and then we solved the model equation analytically. So, the time variation was given as T infinity plus T 0 minus T infinity e to the power minus a t, where a was given as minus h plus h a s upon rho v c. Further, using this solution we developed the phase portrait. Very quickly, the phase portraits looked like this. T, this is the equilibrium solution, then the phase portraits look like this. Okay. This is the general idea that we got in the previous lecture. So, let us continue our discussion. Now, we are asked to develop the phase portrait without explicitly solving the governing equation. This is important. Okay. What we have been asked is to develop the phase portrait without explicitly solving the governing equation. In the previous case, we did solve the governing equation. We wrote T of t equals T infinity plus T minus T 0 minus T infinity e to the power minus a t. And then we saw that okay, what are the extremities which the system can have, what is the exponentially decaying behavior, what is the exponentially rising behavior, and then we drew the phase portrait. Now, the question is, do we need to really solve this problem to develop the phase portrait? In this today's lecture, we will see that in fact, you do not need to solve this problem explicitly to get the same answer. Let us see how. So, our model equation was dt by dt is equal to minus a times t minus t infinity. This was our model equation. Now, we have a bifurcation parameter in this system. In the previous lecture, we in fact saw that for the sake of mathematical completeness, you may actually analyze positive and negative values of a and you see a completely different behavior. So, therefore, in this lecture also we will take up these two possibilities and see what is the effect of a on the dynamics of the system. So, let us imagine that a is greater than 0, which is in fact the physically realizable situation. Your value of a is greater than 0, which basically means that every single property associated with the system is in fact positive. So, let me draw the axis, this is the time, this is the temperature. The first thing which you do is, so this is for A greater than 0, the first thing which you do is you identify the equilibrium solution on this phase portrait, and we know that T equilibrium is T infinity, right. So, let us assume that this is the value for T infinity, this is T infinity, okay, some value of temperature. Now, I can divide this region, I can divide this plane into several regions. Okay. So, I have d T by dt which is equal to minus A T minus T infinity, and therefore, looking at T infinity, I divide this entire plane into two regions. This is region 1 and this is region 2. Okay. So, in region 1 T is greater than T infinity. Okay. The temperature in region 1 is greater than T infinity, and therefore, what is going to happen in region 1, A is greater than 0 we know, and T minus T infinity is also going to be greater than 0, because T is greater than T infinity. So, therefore, what is going to happen to d T by dt? This is going to be equal to negative, which is minus sign, multiplied by A, which is positive, multiplied by T minus T infinity, which is again going to be positive. So, overall dt by dt, which means the gradient, is going to be negative. So, therefore, in this region the gradient is going to be negative. Now, you imagine that you have to draw curves in this region such that the gradient of the curve is always negative, but you have to end up here, because this is the long term behavior, this is the equilibrium solution. So, how will you solve, or how will you draw the curve? Well, you can draw the curve like this. This is one of the curves. Remember how did I do that? I took into the consideration that along this curve the gradient should always be negative, and then second thing, it should end up at T infinity as T tends to infinity, right. So, this is one of the curves, and this will be your T 0 C 1, one of the initial conditions. You can have several of these curves corresponding to different initial conditions and so on. Fine. And if you remember, this is exactly the same phase portrait which we obtained for T 0 greater than T infinity. If you remember from the previous lecture, this portion of the phase portrait was exactly like this. Now, I go for region 2, I have dt by dt is equal to minus A T minus T infinity. In region 2, T is less than T infinity, right. In this region T is less than T infinity, and therefore, what I have is dt by dt, which is equal to minus sign, which is negative, times A, which is positive, times T minus T infinity, which is negative, which means this is going to be a positive quantity. So, the derivative in region 2 overall has to be a positive quantity. Now, the question is how you are going to draw a phase line which conforms to two conditions. The first condition is that the derivative of the line should always be positive, and the second condition is that it should asymptotically reach t infinity as t tends to infinity. I hope you will be able to convince yourself that this is going to be one of the phase lines, and you can draw several of them to make the complete phase portrait, and then you will realize that this is T02 and these are different initial temperatures or initial conditions. And for T0 less than T infinity, you in fact saw that this was the exact same phase portrait that we obtained in the previous lecture. Fine. So, then what do we understand by this? What we understand by this is that for this particular problem or the problems of this nature, you actually do not need to solve the problem explicitly if you merely want to know the qualitative dynamical behavior of the system. And does this phase portrait make sense physically? Well, in region 1, your initial temperature of your system is larger than the equilibrium temperature, the equilibrium temperature being the temperature of the reservoir. So, therefore, with time, so this is the direction of time, with time the temperature of your system is going to reduce. Well, if you have a body which is colder than your reservoir temperature, then what is going to happen? The temperature of your body is going to increase. This is the direction of time, and ultimately all of them will reach T infinity. Okay. Now, you may say that negative time does not exist, negative time. In fact, you can always shift the time to a 0 of your convenience. Therefore, negative time does not exist. Yes, physically it does not, but mathematically this particular space is always available. So, therefore, we draw the complete phase portrait like this. So, let me elegantly draw the phase portrait like this. So, my equation is dt by dt is equal to minus of a t minus t infinity. I will mark the axis as t and capital T. I will mark the equilibrium solution by this dotted line, and this is going to be equal to t infinity, and in fact, you can put t infinity anywhere on this plane. Okay. So, all the axes which are parallel to the time axis can be in fact t infinity subject to the condition that they are physically realizable. And once we have marked all of this, then for a greater than 0, for a greater than 0, the asymptote is this. So, therefore, these are going to be the phase lines, and for a less than a greater than 0 and temperature less than T infinity, these are going to be the phase lines. So, this is the phase portrait. Okay. Now, the question is that for a condition where A is less than 0, okay. So, imagine that there is not this particular system, but there is some system for which you have an analogous model equation and A in that case is less than 0. Then how would the phase portrait look like? Well, we can do that analysis. Let us write d t by dt is equal to minus a t minus t infinity, and now we are trying to develop a phase portrait for a situation where A is less than 0, making the overall coefficient of the exponent to be positive. So, I will again draw the equilibrium solution as this horizontal line, this is T infinity. I will divide this entire phase portrait into two regions, this is region 1 and this is region 2. So, let me do an analysis for region 1 and region 2. So, for region 1, T is greater than T infinity. Again, I am not solving the model equation, all I am doing is I am analyzing the derivative. So, dt by dt is equal to minus a t minus T infinity, which means this is going to be minus sign is negative always, a in our case is less than 0. So, you have negative, but T minus T infinity is going to be positive. So, overall d by dt is going to be greater than 0 or it is going to be positive. So, let us imagine a curve which always has a positive slope, but now the situation is completely inverted. You have an asymptote which has to be T infinity, the equilibrium solution will always be an asymptote, and therefore, the curve should have a positive slope and an asymptote which is T infinity, but the T infinity now will be here. Okay. It will be here. So, therefore, the only way I can draw this curve is if I draw curves like this, and these would be the phase lines. Remember why I could not draw the asymptote for t tending to positive infinity, because there is no way this solution this curve can be drawn with a positive slope. The only way that the slope can be maintained positive and at the same time you have T infinity as the asymptote is if you go to negative time. Okay. Fine. And now for region two, which means t is less than T infinity, my dt by dt is equal to minus a t minus T infinity, which means that negative sign is always negative, a in my case is negative and T minus T infinity is also negative, which means overall the slope has to be negative. Again I have to draw curves such that the slopes are always negative and T infinity is an asymptote, and therefore, the only way I can draw any of such curves is I do this. Okay. So, therefore, for the case where a is less than 0, your phase portrait looks something like this. Now, let us analyze how does the phase portrait change as a function of a. Okay. So, I will need to draw two phase portraits now. This is T, this is capital T, this is T, this is capital T, and irrespective of the A, the value of A, T equilibrium remains the same, right. So, I will draw the horizontal lines corresponding to T equilibrium. So, this is T equilibrium, this is T equilibrium. Now, on the left hand side, I draw the phase portraits for A greater than 0, and for the left hand side right hand side I draw for A less than 0. Okay. So, for a greater than 0, we saw that the phase portraits, phase lines look like this. These were the phase lines, and for a less than 0, the phase lines look like this. Okay. So, let us see the characteristic features of the two phase portraits. When a is less than 0, when a is less than 0, which is the phase portrait you can see on the right hand side, the system diverges with time. Okay. So, the temperature or any associated parameter for that particular system, it blows up to infinity as time t tends to infinity. Whereas, for a greater than 0, remember your model equation already had a negative sign in front of it. So, the general theory remains the same, that for an equation of the form dx by dt is equal to a x, for a greater than 0 your system is unstable or divergent, for a less than 0 your system is convergent or system is stable. So, since this in this particular case your model equation already had negative sign in front of it, for such a case for a greater than 0 you see a convergent system, the solutions converge to the t infinity situation. Okay. So, therefore, we can say that the fate of your system, the value of the variable as time t tends to infinity, depends upon the sign of a. When sign of a changes, the fate changes. And what is the meaning of fate? See, I am not interested in the exact value of the dynamical variable or the rate at which it increases or changes. I am interested in knowing what happens to the final value. As long as my a is greater than 0, irrespective of the initial condition, my final fate is that I am going to end up at t infinity, and this is going to be exactly opposite when when the sign of a changes, you move away from t infinity. So, therefore, you have a stable system here and you have an unstable system here, and therefore, the system has a bifurcation, and the bifurcation parameter is a, and the system has a bifurcation about a is equal to 0. Fine. So, this is the complete phase portrait, and I emphasize again that these phase portraits consider all the possibilities which may or may not include physically realizable properties, and this is quite obvious by looking at this particular phase portrait, that this particular region which you can see here is the physically realizable region. So, therefore, for our particular example you may worry about only the first coordinate where temperature is positive and time is positive, but otherwise as a complete mathematical theory you must know that this is how the phase portraits look like. Now, when we drew these phase portraits without actually solving the problem, can we ensure that these are actually the solution lines? For that, let us do one thing, let us draw these curves and visualize these curves. So, our solution, let us remind ourselves that our solution was t of t is equal to t infinity plus t 0 minus t infinity e to the power a minus a t. Okay, this was the solution, and I will use the online Desmos calculator, graphing calculator, to visualize the solutions. To make it easily visualizable, let us recast this as f of x is equal to a plus b minus a e to the power minus c x. Okay. Due to the syntax which is required in the graphing calculator, we will be using this, where a would correspond to t infinity, b would correspond to t 0, and c would correspond to the parameter a. So, let us draw these f of x is equal to a plus b minus a into e to the power minus c x. This is the equation, and let me tweak around these parameters. So, a was the ultimate temperature. So, let me make it in a range of 200 to 500. B was the temperature. So, let me make it in a range of, again we can keep the range same, 200 to 500, and let me change this to a small limit of minus 0.1 to 0.1. Okay. So, let us see what we observe. Let us see. So, our first condition was that when the initial temperature is greater than the equilibrium temperature, then your solutions would converge at time t tends to infinity, provided your C is positive, right. This was the phase portrait which we developed. So, our equilibrium temperature, let us set the equilibrium temperature at 200, and my initial temperature was say 300, right. So, this is what happens. Your temperature starts with 300, it goes down to ultimate temperature of 200. What is the importance of the parameter C, or in our model equation the parameter A? It gives you the speed with which, or the rate with which the parameter comes down. So, I can make this smaller. As I said, small value of A means slow decay. Okay. This is how it looks like, and you see here in the negative region, negative time, again for the sake of mathematical completeness, the curve looks like this. So, the overall response is like this, and do we see this in this particular mode? Yes, what we saw was you have this, and this is exactly what you see in here also. You see here reducing. Now, what happens when the equilibrium temperature is larger? So, let me make the equilibrium temperature as 400. You see here, you start with some value, say 300, and then you rise. Is this what we also saw in the phase portrait? Yes, we saw in the phase portrait that you actually go like this, and this is the curve which you are seeing this, right. So, for A greater than 0, our phase portraits actually match. What about A less than 0? So, for A less than 0, now you see that your system has asymptote at t is equal to minus infinity. This is what we also saw in our case. So, let me draw what we saw. We in fact saw that the system will have slope which is always negative, and it will have the asymptote at negative infinity, and then the other curve was like this. And then let us see if we saw this thing in the present case as well. I will make this positive, and you see this for this case. Okay. So, negative, the system diverges, and then the system diverges to negative infinity, positive the system saturates, and for this case also the system saturates to infinity. So, I can animate all of these, and then you will see that these are all the possibilities that the system can sample, and you can get the corresponding dynamics. So, let us see what we understood and learned in this particular course. What we studied was that we started with the definition of order of a system, the definition of linearity, the definition of autonomous systems. Then we studied the behavior of first order linear autonomous systems, and then we took up an example which was a physical example of cooling of a body. And then what we realized was that all the principles that we studied for the analysis of dynamics of a very simple equation of the form dx by dt is equal to a x can in fact be realized for a physical system as well. We developed the phase portraits, we invoked the concept of equilibrium solution, we also invoked the concept of phase lines, we understood how to draw the phase portraits and how to draw different phase lines, and also the concept of bifurcation. While we did understand the limitation for one particular set of physically realizable quantities, we also realized that there can be other situations where the other values of the system parameters may be sampled, and therefore, for the sake of mathematical completeness with an expectation of being able to extrapolate similar concepts to other models and other systems, we looked into the complete phase portraits including positive x axis, positive temperature axis, negative x axis, negative temperature axis, and learned the general behavior of first order systems. We will stop here today, and then from the next week onwards we will take up the case for higher order linear systems. Thank you.